Hi there, Professor Huckabee here with your, wait for it, last lecture of Test 1 material. And the best news is that this is actually from a help session or a problem-solving session that was done right before the first exam in the spring semester. So there are a couple questions on here. There's only going to be one video for this lecture because the rest of them were very much the last class specific, so it's less useful for you all. So please enjoy the lecture, or at least the question answering part of it, and let's get to your to-do list. So your to-do list for this Thursday is to do the homework for assignment, as always. Work as many of the chapter 1 and 3 through 3 problems as you can, as well as be sure to complete the practice exam so that you know what you are going to face come next Tuesday, the 15th. And please work the old exams if you can, because that will help you to know a little more what's coming. Don't forget, there's the exam on the 15th, as well as please come to or watch the help session videos and come to office hours if you have any questions. These are times that I devote to making sure that I can answer all the questions that you have. So I'd really like it if you would all come. Last, please have a look at the study guide and the learning objectives that are posted on Canvas. These learning objectives are where the questions on the test will come from. So please have a look at that. That way you are super adequately prepared for our exam. And with that, I hope you all have a nice weekend and you're prepared for the exam. All right, so again, silly meme time, but it does give us an idea of a question that we've kind of touched around so far, and that is this idea of communication, and communication about molecules and compounds. Because, like our friend Eddie Murphy says there, you know, cannabis is just heavy sugar, right? No. And if you look at these chemical formulas I've shown you here, it's pretty instructional to think about. Just writing the elements up there doesn't really give you a whole lot, unless, of course, you're talking about CH4. Because CH4 is the molecular formula and tells us the structure. There can only really be one CH4, right? But as soon as you start getting a little more complex, adding another carbon, adding an oxygen, you can make a lot more different structures, and these are just a few. Okay, so in your mind, how many different structures of C4H7N2 do you think you can make? Is it more than 5? Is it more than 10? More than 20? It's a lot, frankly. And they have a bunch of weird structures that you maybe haven't thought of and maybe haven't encountered yet in this class. And these are just some. I really just pulled a few off there. So looking at the formula gives you some information, but it doesn't tell you, for instance, which of these constitutional isomers you're looking at. Constitutional isomers is something we talked about earlier, and I'm kind of refreshing your memory because it's a thing that we'll encounter later, but it's this idea of having the drawing as the real representation of the molecules. Even if it's just bond line structures, is a lot better than just writing what the molecular formula is. No? All right. So let's open the floor for questions then. You can throw up a hand and I'll call on you. All right, I see one here first. Yeah.
Can you go back and talk about the molecular orbital theory and like LUMO and
Yeah, I can do that. So the question is, I'm going back to talk again about the MO theory and the idea of HOMO and LUMO in terms of molecular orbitals. So what I'm going to do is I'm going to grab my notes from that lecture. That way I can be mentally on the same page as well. Go. Yeah, all right. Cool. All right, so if you remember, in the very beginning of the class, we were talking about different ways to talk about bonding. You had valence bond theory, and you had molecular orbital theory. In molecular orbital theory, we were talking about mixing of different orbitals to make a bond, right? And all right, good. So one example of that is bringing together two hydrogen atoms. They're atoms because they have the electron there. Bringing them together to make H2. This is the simplest MO theory example we can give. So when you bring these two together to make a bond, you can think about it this way. You have two 1s orbitals, and they both have an electron. We'll just say one is spin up, and we'll say one is spin down. Because, you know, they like to be paired, and it doesn't matter. It just makes our lives a little easier at this point. All right, so when you bring them together, get my pens ready here. When you bring them together, we're going to mix the two orbitals. And when you mix two orbitals, what you end up getting is two orbitals back. So we'll make one at higher energy and one at lower energy. And the reason why we put one higher and one lower is because you're going to get a little stabilization. And by get stabilization, I mean the energy will be lowered by some amount because there's constructive interference between those two electrons. But that energy that you gain, you also will have another energy level that will be offset due to destructive interference. Because remember, an electron is like a particle and a wave. So if you think about an electron, you have equal probability of having something in one phase as you do the other, especially in an s orbital. So you have a stabilization, a constructive interference interaction to lower the energy, but also a destructive interference interaction that increases the energy of the other energy level. So these are our two energy levels that we made from mixing two 1s orbitals. Now that we have our two energy levels, we simply add in the electrons, just like we normally would do for any other atomic electron configuration. Which means that following our three rules, Hund's, Aufbau, and the Pauli exclusion principle, we end up with one energy level that has electrons, both of them, and the other that doesn't. So what this means is that the one with electrons, we're going to do this in blue, this one becomes the highest occupied molecular orbital, and that's where we get the term HOMO from. And this one over here on top, the higher energy with no electrons, becomes the lowest unoccupied. Sorry for my handwriting. It is not good. There we go. So that becomes the LUMO because it has no electrons, meaning it's unoccupied, and of the ones we're looking at, it's the lowest energy. So in this very simple example, we have one that is the HOMO because it has electrons and one that is the LOMO because it doesn't, right? But you can also extend this theory to larger systems or to different bonding patterns, which is probably what you were getting at more with your question in the double bonds. So thinking about this exact same thing, let's mix orbitals for this molecule. So we have some H's all around. Yeah, I thought you probably thought you were going to get away with not learning anything new, right? Well, you were wrong. All right, so we're going to do butadiene, which I think actually is the example I should have started with, because I think it is pictorially a much nicer example, and perhaps it can give us all a little better understanding of just how to build these molecular orbitals. All right, so hopefully everybody has the structure of butadiene drawn. I'm going to draw it in bond line structures on the next page, just so that we're clear. Okay, we're going to look at, let's see, put the face down. There we are. All right, we're going to look at this molecule. Right, everybody on the same page? Good. Okay, so butadiene has 1, 2, 3, 4 carbons that are in conjugation, which means we're going to be mixing not 2 orbitals, but this time 4. Does everybody see why there would be 4? There are 4 pi electrons because there are 2 double bonds. So 2 double bonds equals 2 sigma and 2 pi bonds. Everybody remember that? Good. Each pi bond has how many p electrons? Do you guys remember? Ooh, I don't know. People seem unsure. In fact, I don't see any answers. 1. I see some 1s. P electrons per pi bond. I really just saw the 1. Okay. Pi bond has what? 2. That's right. A pi bond has 2 electrons. And you know that because it's a full line. So each pi bond equals 2 electrons. And we also know that because each carbon contributes 1 p electron to a pi bond. Yes? Sigma bond is also 2 electrons. A sigma bond is also 2 electrons. And if you ever become unsure about that, you can draw out the whole structure. And remind yourself that every bond means that the carbon is sharing an electron with whatever it's bonded to, whether it's a single or a double. So you can always piece out, okay, this CH bond is 1 electron from the carbon and 1 electron from the hydrogen. So every carbon actually looks like this still. As long as it's neutral, of course. All right, so back to butadiene. We have how many pi electrons now? 4, right? 4 pi electrons. How many p orbitals are we going to mix? 4 p orbitals, 1 for every carbon, right? Okay, so let's just start with that. So energy is increasing, as always, and we're going to mix. We'll say we'll mix these 2 p electron or 2 p orbitals with these 2 p orbitals, just because I like it to be symmetric. So why don't we do like this? Each is a p orbital, each has an electron, and it's going to be mixing with these 2 p orbitals. From different carbons. And I'm just drawing them here. It doesn't actually matter where you place them. You'll see from the mixing that in this case it's going to make it look nicer, but you could just put them all to one side or the other, just as long as you have the concept down. In this case, it doesn't matter. So when you mix 4 orbitals together, how many orbitals do you get out? Remember, it's like a blender. You start with 4 limes for your margarita. When you get it, when you end up with a margarita, how many limes do you have left? You still have 4, right? Let's say you get to drink the limes this time. So here, we're going to have 4 orbitals. So remember in our previous example where we mixed 2 and we got 1 that was high energy and 1 that was low energy? Why don't we do that to start with? Oh, let's do it in blue. It's a little easier to see. I like some good color contrast, if it does contrast. There we go. So we have one very high and one very low. But that's only two, right? So we need two more. So why don't we split the difference, and we'll do one that's a little lower and one that's a little higher. So now we're left with 4 molecular orbitals. Remember, it's molecular orbital theory, so we mix 4 atomic p orbitals to get 4 molecular orbitals. Right. So now we use our 3 rules for putting in electrons, just like we normally would. And we'll do it in black. So we have 4 total. So let's start 1. And the rules say we have to pair that one up, so 2. Then we go to the next highest energy level, and we add 1. And then we have to pair that one up. And we're out of electrons. So you notice that there are still the low energy molecular orbitals that have electrons in there, but then there's the higher energy orbitals that don't. And here, let's see, let's number these for fun. We'll call this 1, 2, 3, and 4. So now it's time for class participation. Yeah. Who here thinks that number 1 is the highest occupied molecular orbital? Okay. What about number 3? What about number 2? Okay, good. Number 2 is the highest occupied molecular orbital because it is the highest energy orbital that has electrons. That's all that means. See how energy is increasing going up? You just find the highest one that has electrons, and that's your HOMO. All right, so if that is the HOMO, what is the LUMO? Is it 4? No, it's 3, right? 3 would be the LUMO because now, in our energy scale, it is the lowest unoccupied orbital that we have. Does that make sense? Yeah, good. I'm seeing some nodding. That's great. So we'll say that number 3 equals the LUMO. So then, I think this was part of the original question, but to really take it home, now we need to talk about what this actually means for the molecule. We have to do the drawings, right? Because in our drawings of the original molecule, this doesn't tell us where the p electrons can be found, right? This is just showing that it's in conjugation. So now we need to look at each of these 4 and find out where the electron density is. So let's draw in our p orbitals. This always takes a little bit of time. Okay, so everybody here is on the same page with me of why I drew 4, right? Yeah, it's because we have 4 molecular orbitals, and every little structure I drew corresponds to one of our energy levels, right? These numbers are those numbers. Good, yeah, we're all on the same page. Great. So, what would be the lowest energy configuration? Would it be one where they're all mismatched and you have no overlap? Or would it be one where they all have overlap across? It'd probably be that one, right? So why don't we mark the tops in blue and the bottoms in red to show that. What about the highest energy? You're talking about the worst bonding configuration. That would be the one where they're all mismatched, right? There's not a single overlap there. So let's go ahead and write those in. All right, that's good. Now for the other 2. And these are the most important, right? Because these are the HOMO and LUMO orbitals. If you notice, in number 1, there's complete overlap and there's no place where it's discontinuous. If you notice in number 4, there are 1, 2, 3 places where there is no overlap. So it seems like if 0 is the lowest energy and 3 is the highest energy, maybe it makes most sense to try to make the next 2 have 2 places where it misses in the overlap and the other having 1. Where 2 would be the highest energy and 1 would be the lowest energy. You kind of do stepwise that way because you're breaking overlap, which increases energy. So if we just draw that in before we do anything else, and keeping the molecule as symmetric as possible, I think we would end up with something like this. So to have 1 dislocation, it should probably be in the middle, right? And then to have 2 dislocations, and to have the molecule still be as symmetric as possible, we would put them here, like that. Does everybody see how that's the most symmetric way to do it? And then we would just color them in. So there you go. That would be your HOMO number 2. We'll just put a star there. And your LUMO number 3. And that's what the electron configuration or the electron density across the whole molecule would look like. So now you've gone from seeing a drawing of a random molecule that has configuration to going step by step through finding each of the molecular orbitals and finding the HOMO-LUMO energy level of each. So is that a little more clear now? Yeah? Does everybody agree it's a little more clear? Yeah, I'm seeing some shrugs and some nods. All right, well, at least there are more nods than shrugs. I'll take that. All right, what about the next question? Next hand. Got one here. Yes. You know what? Now that you mention it, maybe it's a good idea to go and do the homework before we go any farther, because the homework had this type of question on it, and we can just make the key for it, and I think it'll be really helpful. Because the answers, or the homework, did not go quite as well as I hoped, honestly. Okay, so let's save this guy as a key. Good. And we'll just open the key. Great. Whoop. Well, that's not helpful, is it? Export as PDF. There we are. Yeah, all right. Okay, here we go. So now let's make the key together, and then we can, the first question here, I think will be an answer to what you asked. Okay, so in 1, it says to find the most acidic proton. And to find the most acidic proton, you can actually use ARIO. Because if you use ARIO, what does that tell you? It tells you what the most stable conjugate base is, right? Do you remember what the most stable conjugate base also means? The strongest acid. I heard it. I was happy I actually heard it. It means the strongest acid as well, which means if you go through your ARIO rules and you find the most stable conjugate base, you will find the most acidic proton at the same place. Okay, does that make sense? In the first one, the one that has an amine and an amide. This guy. We go through the ARIO rules first. And to do that, we generate a conjugate base of each part of the molecule, right? So we'll just do like this. So this would be the conjugate base of the top part, and the bottom part, the conjugate base, looks like this. All right. So in these conjugate bases, do we have any differences in what the atom is? No. Do we have any differences in any resonance that there might be? Yes. Okay. So A, that was a nothing. R, yes. Which one has resonance stabilization? The top one, right? Because it's an amide, and you can make a resonance form that includes the lone pair into the amide carbonyl, just so that we can see that. There we are. And there were 2 lone pairs there. Great. So the structure for that resonance form would look like this, where now the negative charge can be delocalized over to the oxygen, and so that conjugate base is more stable. Because the conjugate base is more stable, that is also the most acidic proton, or the place for the most acidic proton. So that's why the answer for that one is the top one. All right, so some of you might have noticed that there was a little trick to the homework because there were 4 questions. And yes? Oh, this guy? Oh, that was so this was supposed to be like that conjugate base. Yeah, sorry about that. Just for clarity, this guy is this conjugate base. Yeah. Sorry, I definitely should have made that clear. Yes? Yes, I certainly can. A means atom, and what that means is, I'm going to go back here. What this means, I'm going to use this screen here on the right. What this means is, as you go right in the more electronegative atom direction, you are more able to stabilize a negative charge. So because of that, those atoms are not so bothered by having a negative charge. Same goes with as you go down. As you go down the periodic table, the atoms get bigger, and so you can just stabilize a negative charge because there's just more room. And that's why we call it atom, because that's really the only difference in what the 2 things.